In this video, we move past the concepts to come up with the equations that we'll use to make calculations and apply the worm-like chain principle to understand strain hardening fibers and materials. So first we consider what happens to a worm-like chain without force. So recall that when we talked about worm-like chains, we said that we determine a persistence length, where we define the persistence length as the length at which there is an E-fold decay over the orientation of the ends, so that they go from being oriented the same way to totally disoriented relative to each other. And if the length is much less than the persistence length, we have a rigid rod. If it's comparable, a flexible rod. Whereas a long fiber that's much longer than the persistence length is a worm-like chain. This makes sense. You can think of the persistence length as the contour length along something at which there's a very significant bend when it undergoes thermal fluctuations. So a short one is straight and a long one is bent around many times and looks like a string. So the time averaged root mean squared distance is the square root of the square of the vector, and that is the square of the vector now is a scalar amount, so the square root is scalar. So we still have units of length, but we've gone from a vector to a scalar. And this is important because as this thing rearranges, the end may point in any direction from the beginning to the end. They can be in all directions as the thing orients around different ways during random fluctuations. But the average, by squaring it, we're not worried about the direction, we're just saying the average length. Now, statistical mechanics that are way beyond this class can be used to show that the following provides an equation for the worm-like chain length in the absence of force. The square root of twice the contour length times the persistence length, and then times, and the rest of this depends on the ratio of the persistence length and contour length. 1 minus LP over L naught times 1 minus exponent to the minus the inverse, L naught over LP. So you can also see, and this is true at all L naught. So at very short L naught, we will see that R, RMS, goes to L naught. That's at L naught is much less than LP. And it can also be shown that at L naught is much greater than LP, then the X root mean square is approximately just so that all of this stuff becomes 1. And it's the square root of 2 times L naught times LP. So now we'll apply this theory to a specific question. We'll ask here about an actin filament. We're told it's made up of globular proteins. The cross-sectional geometry can be estimated as a circle with diameters 5.5 nanometers. And our question now is, what's the average end-to-end length of an actin filament that has these various lengths? We'll start with 0.2 microns. So in order to ask this, we learned in the last slide that the end-to-end length depends on the persistence length. And so we need to first calculate that. And in this case, we've been told something about the geometry of the material. This allows us to calculate the persistence length from the flexural rigidity and from thermal energy. We know we're able to use here that the Young's modulus of proteins is around 2 gigapascals. We then calculate the moment of inertia from the cross-sectional diameter, and that comes out to be this value, and then the flexural rigidity is the product of those two, which comes out to this when you plug those in. And then lastly, we need thermal energy. We aren't given a temperature here, but in general, if you're not given a temperature, no one thought to mention it because, of course, they're just doing experiments at room temperature. So we just plug in thermal energy at room temperature here. And that then creates this final answer, that the persistence length is 1.5 times 10 to the minus 5 meters, or 15 times 10 to the minus 6, that is 15 microns. We could also have looked this up, or one could have done an experiment and measured it directly. And in fact, experimental measurements reported persistence lengths between 12 and 18 microns, also reminding you that just doing an experiment doesn't necessarily give you an exact answer either. There's often some calculations and some assumptions that go into the experiments that create a variable length as well. Now that we have the persistence length of 15 microns, we can go ahead and ask our questions about the average end-to-end length, that is R root mean squared, of actin filaments of 3 different lengths. We'll start with 0.2 microns. So our first question is to compare L naught, 0.2, to LP, 15, and we see that it's much less than. So that tells us this looks like a rigid rod, and in fact, if we had plugged in L naught to S and measured to what degree the average cosine of the difference between the two ends had changed, we'd see it was still almost 1. So this fiber is a rigid rod, and the average end-to-end length is just the contour length, 0.2 microns. So that was this situation, straight fiber. Now, our second question was, what if L naught is 10 microns? So 10 microns is pretty close to 15 microns. And in fact, had we plugged this in here, we would have seen that the exponent of the minus L naught divided by LP of the ratio of the contour length to the persistence length is about 0.5. So our orientation, they've gone from being completely oriented the same way about halfway down to being unoriented. So this means there's still some orientation. This might be the set of conformations you get of this fiber. And of course, they can also go up and down. I should mention that they're not all bent uniformly. And so this thing, you expect to get a number that's close to 10, but it can't be longer than 10. It's generally going to be shorter than 10 because these are bent a little bit. And we have to use this full worm-like chain equation here, or this full equation, because we can't do that estimation where we said this thing in the middle went to around 1. So we just need to plug in all the values into this, and when we do that, we get 9 microns. And so in fact, we see that R root mean squared is less than L naught, but not by that much. It's only a little less than. So here it was equal to L naught, now it's a little less than. Then our last question is, what about a contour length of 500 microns? So in this case, 500 is much greater than 15, and in fact, if we had measured that cosine, we'd see that we went down to 0. The two ends are completely disoriented relative to each other. So now we can use the root mean squared. We can use the estimate of the square root of 2 times L naught times LP, and we get 122 microns. And so that is a situation where we have something that is curling around like this. So the next thing we learn about is, what are the mechanics of these worm-like chains? So far we just estimated their end-to-end distance without force, but now we ask, what happens when you apply force? We're now interested in the end-to-end length in the direction of force. That means if there's a fiber that's curled up so that that's the start and end distance, and we pull on it that way, that it's this distance here that we care about, because that's the dot product of the end-to-end length R with the force F. So it turns out that the force required to maintain this length R is given by this equation here, which is really a mess, and you'll be really glad I don't make you memorize it. So note here that it is proportional to the thermal energy divided by the persistence length, and then there's this function here that depends on the ratio of the end-to-end length to the contour length. That is the fractional extension. So if you had something that was coiled all the way out, that's L naught. and the fractional extension is how far along you are there. So this plot down here shows you R relative to L naught. So the fractional extension here, R over L naught, is equal to 1 as you get fully extended. So we're interested in two things here. The first one is, what is the spring constant of this at low extensions? Because that will determine a lot of the properties of a worm-like chain. And the second thing is, what happens when we get to high extensions? So if we use a first-order Taylor approximation, or the first-order Taylor expansion of this, you can show that for sufficiently small r, that the force is going to equal this prefactor here times r over L naught, which means the spring constant, the thing you would multiply by r, is this value 3 times the thermal energy divided by 2 LPL naught, which interestingly is twice r root mean squared, because that was the square root of 2 LPL naught. We say this approximation is reasonable while r is less than 1/3 of L naught, that is through about this range here. That's a reasonable approximation. After that, it deviates from it. And in fact, you can see, looking at the full equation, that this will approach infinity as r approaches L naught. And that means that this worm-like chain exhibits strain hardening, that it goes above that spring equation for higher elongations. Now we'll go back to our actin filament example and ask how the shortest and longest actin filaments act under force, that is, what are their spring constants. Because the persistence length was 15 microns, the shorter one is much less than the persistence length. Its contour length is less than, so it acts like a rigid rod. If we want to know the spring constant of a rigid rod, we have to go back to our axial load, all the way back to week 3. So the axial load on a rod is the spring constant is EA divided by L. And remember, this applies, we are also asking through what strain are these accurate. This applies up to the strain that globular proteins can withstand, which is about 3%. So we just plug in for pi r squared, half the diameter for r. We plug in the Young's modulus we used before, and this results in a spring constant of about 0.2 newtons per meters. Then the next question was, what about for the very long actin filament? We certainly expect a long one to be softer. We already know that axial rods get longer. But in this case, not only is it a longer chain, but it's no longer an axial rod, because L naught is much greater than LP. It's a worm-like chain. So before we were stretching that, now we're stretching this. And what this means is that we can stretch it a long way without even stretching that fiber, without stretching the material. All we have to do is reduce entropy in order to straighten it. We don't have to worry about any enthalpic change of stretching or bending or straining the material itself. So we use the worm-like chain, because this is a worm-like chain, we use that spring constant we calculated. Remember, that is good up to r is less than 1/3 of the contour length, which here is 167 microns. And so we can say that's a strain of about 0.3. I guess we got that even from the first part. And so this calculates out, when you plug in all of the values into this, to be 5.5 times 10 to the minus 13 newtons per meters. So we notice here that this is much, much softer. In fact, it is about 12 orders of magnitude softer. So this really makes a big difference when you can straighten a material rather than stretch the material. So this example illustrates how we can use properties of worm-like chain to understand the behaviors of fibers, nanoscale fibers of very different lengths.